Welcome to Chapter 1 of Probability Theory and Stochastic Processes. Probability is the mathematical language for uncertainty, and in materials science, it underlies defect counting, measurement error, and equipment reliability. In this chapter, we build the vocabulary. We define discrete and continuous random variables, meet the probability mass function and the probability density function, and see how expectation, variance, and moments compress a whole distribution into a few numbers. Then we tour 4 workhorse distributions: binomial, Poisson, normal, and exponential. Finally, we put everything into Python using scipy.stats. Only calculus basics are assumed. Let's start with a die. A discrete random variable takes countable values, and its probability mass function assigns a probability to each one. The probabilities must be non-negative and sum to 1. A fair die is the simplest example: 6 outcomes, each with probability 1/6. From the mass function, we can build the cumulative distribution function, which accumulates probability as we move to the right and rises in steps. And from the same table of probabilities, we compute the summary statistics directly. For the die, the expectation is 3.5, the variance is 2.9167, and the standard deviation is 1.7078. Continuous random variables take real values, so no single point carries positive probability. Instead, we describe them with a probability density function, and probability becomes area under that curve. The probability that x lies between a and b is the integral of the density from a to b, and the total integral over the whole line equals 1. Take the uniform distribution on 0 to 1. The density is flat, so the probability of landing between 0.3 and 0.7 is simply 0.4. The cumulative distribution function is the integral up to x, and here it rises as a straight line. 2 numbers usually carry most of what we need to know about a distribution. The expectation is the probability-weighted average, a sum of x times p in the discrete case, an integral of x times the density in the continuous case. The variance measures spread. It is the expected squared deviation from the mean, and the convenient computing form is the expectation of x squared minus the square of the expectation. These are the first 2 of a family. The kth moment is the expectation of x to the power k uniform. Normal, exponential, and beta distributions each have their own mean and variance. The binomial distribution describes the number of successes in n independent trials. Each with the same success probability p, its probability mass function multiplies 3 pieces. The number of ways to choose which k trials succeed, p to the power k for those successes, and 1 minus p to the power n minus k for the failures. The expectation is n times p, and the variance is n times p times 1 minus p. This is the natural model for quality control. If a product has a 2% defect rate, and we inspect a lot of 100 items, the count of defective items is binomial. The Poisson distribution counts rare events over a fixed interval. Its probability mass function is lambda to the k times e to the minus lambda, divided by k factorial, and remarkably the mean and the variance are both equal to lambda. It arises as the limit of the binomial when n grows large, p becomes small, and the product n times p stays fixed at lambda. With 100 trials at probability 0.03, the binomial and the Poisson with lambda equal 3 nearly coincide. In thin film deposition with 3 defects per square centimeter, over 5 square centimeters, the probability of 10 or fewer defects is 0.1185. The normal, or Gaussian, distribution is defined by 2 parameters. Mu sets the center, and sigma sets the width. Changing mu slides the bell curve along the axis without changing its shape. Changing sigma makes it narrower and taller or broader and flatter. Its most quoted property is the 3 sigma rule. About 68% of the probability lies within 1 standard deviation of the mean, about 95% within 2, and about 99.7% within 3. Any normal variable can be converted to the standard normal with means 0 and variance 1 by subtracting mu and dividing by sigma. That transformation is called standardization. The exponential distribution models the waiting time between events in a Poisson process. Its density decays as lambda times e to the minus lambda x. The mean waiting time is 1 over lambda, and the variance is 1 over lambda squared. Its signature property is memorylessness. Given that you have already weighted s, the probability of waiting a further t is exactly the same as it was at the start. Past information tells you nothing about the future. If equipment fails at a rate of 0.1 per day, the mean time between failures is 10 days, and the probability of a failure within 7 days is about 0.50. In Python, scipy.stats provides more than 70 probability distributions behind one unified interface. Create a frozen distribution object with its parameters, then call the same methods regardless of which distribution you chose. Use PDF for the density, CDF for cumulative probability, PPF for percentiles and confidence limits, RVS to draw random samples, and mean, var, and STD for the summary statistics. That uniformity is what makes exploratory work fast. In materials science, 3 distributions appear repeatedly: liable for the strength of brittle materials, log normal for particle size, and gamma for waiting times. A ceramic with shape 10 and scale 500 megapascals is a typical strength model. Let's recap. Discrete random variables are described by a probability mass function, continuous ones by a probability density function, and in both cases, the cumulative distribution function accumulates probability. Expectation and variance compress a distribution into a center and a spread. The binomial counts successes in fixed trials, the Poisson counts rare events, the normal distribution gives us the 3 sigma rule, and the exponential distribution gives memoryless waiting times. And scipy.stats makes all of them one line of code away. In Chapter 2, we ask what happens when we average many random variables, the law of large numbers, and the central limit theorem.